And finally, we are going to model a situation when one of the species is a predator and the other one is prey. First of all, I suggest that you pause the lecture and try to figure out in this example which of the two variables represents the wolves and which represents the moose. Okay, now I will explain. So the coefficient at xy in the equation for x is positive, meaning that the presence of y is good for x. But then the presence of moose is good for wolves, because wolves eat moose. So therefore, x prime has to be wolves. And at the same time, the coefficient at xy in the equation for y prime is negative. It means that the presence of x is bad for y. It makes their population grow slower. So which means this has to be moose, because moose get eaten by wolves. But notice that at the same time, the coefficient at x in the equation for x prime is negative. It means that without y, wolves would disappear. They do not have any external source of food. And the coefficient at y in the equation for y prime is positive, meaning that without wolves, the moose would just grow unboundedly, which in practice is impossible, of course. So let us find the equilibrium solutions. Now, from the first equation, either x is 0 or y has to be 125. And from the second equation, again, either y is 0 or x is 40. But if in the first equation x is 0, then, so let me write. If x is 0 in the first equation, then y has to be 0 in the second equation, so which means there are two critical points, 0, 0, and 40 and 125. Here is the Jacobian matrix. And the little challenge for you is to find the types of these critical points without calculation. So I suggest that you pause the lecture and try to do it. And now I'm going to explain. So let's do first 0, 0. If the point is 0, 0, then these parts disappear, and the rest is a diagonal matrix with a negative number on the diagonal and a positive number on the diagonal, so which is a saddle point. So this is saddle point. Now let's do 40 and 105. So notice that if it is 40 and 125, then the way that we found the number is 40. 40 was the number that made this equation equal 0. And 125 was actually a solution of this equation. So which means that the numbers 40 and 125, the way that we found them is because these two entries of this matrix are actually zeros. So which means that the matrix becomes like this: 0 here, 0 here, positive number here, negative number here, and of course this is a center. Well, let us see. Yeah, it is true. Here is the face portrait, and I suggest that you try to figure out what the other graph is. And let me explain. So the other graph is a bit strange. So here, this axis is t, but the vertical axis is actually either x or y, depending on whether you look at the blue curve or the red curve. So the red curve somehow is oscillating between 30 and 50, and on the left graph it corresponds to x, so x oscillating between 40 and 50, which means that this is x, and y is oscillating between, well, much bigger numbers, which means that the blue one is y. So here we plotted x and y on the same plane together just to see how the oscillations look like. And notice that this is actually consistent with the our intuition, because x is the predator and y is the prey. And so x is the predator, so this is wolves, and y is the prey, so this is moose. And notice that initially the population of moose is small, and if it is small, then wolves do not have enough food, and the wolf population is declining. But if the wolf population is declining, it means that there are less predators who eat moose, so the moose population is growing to a certain point, because at a certain point the moose population has grown sufficiently large so that wolves get a lot of food and the wolf population is going to grow. But then the moose population eventually still grows, but to a certain point, because at a certain point the wolf population is just too big, and then they start eating moose more actively and the moose population is dropping. But when the moose population is dropping, at first it is still large enough so that the wolf population is still growing, but then it's not enough food for wolves and the wolf population is dropping. But the wolf population itself is still sufficiently large to kill off all the moose, and the moose population is decreasing to a certain point, but then the wolf population is becomes too small, and then the moose population is growing again, and so on. So it is kind of, I think, very reasonable prediction that the model, so that both wolves and moose are going to grow, well, to change in cycles. And the peaks of the wolf population is going to be a little bit later than the peaks of the moose population. Well, but then notice that if the linearized system has a center, it doesn't yet mean that the original system also has a center. It seems to be this way from the plots, but theoretically we didn't show anything. But we can do it actually. So we can, in this case, we can just calculate the trajectories. So we can divide y prime by x prime, and the equation that we saw. So the equation that we got, dy dx equals this. So notice that this is actually a separable equation, and we can separate the variables, and we can solve it. We can integrate. Since both x and y are positive, so we don't need to do a logarithm of absolute value of x. We can just do logarithm x itself and logarithm y itself, and here is the solution. So in other words, if we move everything with x to the left-hand side, then what we just saw is that trajectories are curves defined by this equation. Finding an explicit expression of y for x or of x for y is just impossible, but we can plot a few such curves in, say, in Desmos calculator, and I suggest that you do it, and you see that they are indeed closed curves, but I haven't proved that they are actually closed curves, but I suggest that you try to do it at home. It is possible to prove that these curves are actually closed curves. Well, anyway, so of course the choice of specific constants is not important here. So any system of this sort is going to look like this one, positive coefficient at xy for the predator, negative for the prey, and negative at x for the predator, positive for the prey. And then there will be one equilibrium with both species present in the system, and the equilibrium is a center point, and every trajectory is a closed loop around it. So the functions are going to be periodic oscillations, and the maximum points for the prey are going to be a little bit ahead of the maximum points for the predator, meaning that once prey reaches its maximum, it starts declining, and then predator reaches its maximum slightly later. Of course, you can make it more complex. For example, you can, as compared to the pure predator-prey system, the simple one, you can include this logistic term into the equation for the prey. So what does it change? Now, I mean, what we did, we introduced the carrying capacity into the prey population. But essentially, what it affects is that now the phase portrait is very different. Instead of cycles, we see an asymptotically stable, asymptotically stable point. It's not very clear whether it is a node or a spiral point, which we can confirm analytically. We can calculate the Jacobian matrix, and then we can substitute the x and y from the critical point into the Jacobian matrix. And here is the matrix. And then I'm skipping the details, but I think you can recover. So you can take the determinant, calculate the trace, and see that it is a nodal sink. It is not a spiral point. And a little bit of a challenge for you is it possible that for some other values of constants, the equilibrium point is a spiral sink or an unstable critical point?